Hi, my name is Escaraferjo Antonelli. This is the executive presentation of a video of the Unit 4, and the topic is colligative properties. We today we will study the properties of solution contains non-volatile solutes, which are decreasing vapor pressure of a solvent, and the lower of the freezing point, increasing the boiling point, the osmotic pressure. These properties are called colligative. They depend only of the number of the particles in the solution and in no way on alternative. As we shall see, this is the essential attribute of the phenomena mentioned above, at last in dilute solutions. Theoretically, it's common to subdivide the solutions into non-electrolytes and electrolytes. In the first case, the dissolved solute remains in molecular form without charge, and those not show a tendency to dissociate into electrically charged ions. In these solutions, certain general laws were established that we'll discuss below. On the other hand, in the electrolytes, the solute dissociates to a greater or a lesser extent into the ions. This increasing the number of the particles in the solution, and the behavior of this with respect to the certain properties of this for this reason change and requires the modification of the simple laws deduced for non-electrolyte solutions and non-electrolyte solutions. The colligative properties for electrolyte solution deserve seriously considerations because they provide us with valuable methods of determination of the meaning of the molecular weight of dissolved substance and possibility of the evaluating a certain number of thermodynamic quantities for a large importance. Here we mainly propose the present principles basic include this use for the determination of the molecular weights of the solutes. First, we'll see the solvent vapor pressure decrease. A solid solute lowers the vapor pressure of a liquid solvent in which it is found. This decline is easily understood if we take into account Rolle's law, demonstrated in the previous chapter. If we designate by M the mole fraction of the solvent and that of the solute, P0 the vapor pressure of the pure solvent, and P that of the solvent vapor over of a given solution according to Rolle's law is given by the next expression. M is in a solution is always less than unity. P must be less than P0, and consequently, the solution of a solid in a solvent it lowers of the vapor pressure than later relative of the pure solvent. When the solid is not volatile, it does not contribute to the total vapor pressure, and therefore equation 1 also gives us the vapor pressure for the solution, which in this case is due for the solvent alone and always less than P0. The magnitude decrease and increase P is the next expression. uh, where we can see the increase of P and the decrease in P0. According to the equation 2, the decrease in the vapor pressure of the solvent depends on both of the both the vapor pressure of the solvent and the mole fraction of the solid. In other words, it's a function of the nature, solvent, and solute concentration, but not the nature of the latter. However, if we consider the relative of pressure vapor, that is the expression increase of P, it hides the P0, then from the equation 2, we have the next equation. It depends only of the mole fraction of the solid and is completely independent of the both nature of the solid and the solvent. Equation 3 from the Rolle's law for solution of non-volatile solids shows that the increase in question is a property colligative because it depends solely on the concentration of the solid. The equation 2 and 3 can be used to calculate the decrease of the vapor pressure on non-volatile solids solutions, or well, knowing what what that they are used to determine the molecular weight of the solvent substance. Increase the boiling point of the solutions. Solutions contain non-volatile solids boil at temperatures higher, and those are pure solvent. The difference between the points boiling and point of solution and the solvent of constant pressure established. It's knowing of the boiling point, which depend on of the nature of the solvent and the concentration of the solid, but it depends at the least in the solution of the nature of the solid as long it does not ionise. This increase easy understand. This increase is easy to understand on the decreased vapor pressure, and it's a direct consequence of it. Uh, we consider the vapor pressure compared in the next diagram. The curve AB presents the vapor pressure of the pure solvent as a function of the temperature. The vapor pressure of the solution is for all temperatures lower than of that of the solvent. The vapor pressure temperature curve as the solution must be low that of the pure solvent. In the order of the region, the boiling point corresponding to the certain pressure exerted to the P0 solution. It must to be heated to temperatures at which the respective vapor pressure equal are the confinement. As the diagrams points out, can reach the pressure of the P0 at the temperature T0, but the solution must rise T greater than T0 before the same pressure is reached. By applying the Clausius-Capellarian equation and Rolle's law to the condition described in the figure, it's possible to deduce the relation between the rise of the boiling point of the solution and its concentration. Since points E and file F lie on the vapor pressure curve of the solution, both are given by the Clausius-Capellarian equation, where P and P0 are the vapor pressures for the solution at temperatures T and T0 respectively. HV is the head of vaporization per mole of the solvent from the solution. If it's dilute, that heat is essentially equivalent to that vaporization per mole of the pure solvent. Decrease on the freezing point of the solutions. As a dilute solution is cooled at temperature is eventually reached at which the only solid begins to separate. Temperature where such separation that begins is known as the freezing point of the solution, which in a more general way is defined as the temperature at which a particular solution is in equilibrium with the solid solvent. Solutions freeze at lower temperatures than the pure solvent. Lowering the freezing point is again a direct consequence of the decreasing the vapor pressure of the solvent by the dissolved solution. To realize this fact, let's just consider the vapor pressure temperature diagram in which AB is the sublimation curve in the of the solid, while CD is the vapor pressure of the pure solvent liquid. At the freezing point from the last fact, the solid and the liquid phases are equilibrium, and consequently, both must have identical vapor pressure. The only point in the diagram at which both forms from the pressure solvent are equal to the vapor pressure is at B, and the intersection of the AB and CD for the therefore T0, which correspond to B, must be freezing point for of the pure solvent. When a solid dissolves in it, there is decrease in the vapor pressure for later, and there is no longer equilibrium at T0, but it's reached again the vapor pressure curve of the solution cups of the sublimation curve. And then we will have the freezing point on the solution. The sum of the pressure of the solution EF is lower than of the pressure of the solvent. The intersection of EF and AB occurs the only point so as E for which the temperature then less than T0. For this reason, any solution must have freezing point T lower than the solvent T0. The freezing point depression of the solution is defined by increase of T is equal to T0 plus T. And the present the number of degrees in which that point is less than that of the pressure of the pure solvent. The magnitude of the increased T increase of T depends on both the nature solvent and the concentration of the solution. When things are diluted, the increase of T value varies linearly with the concentration without depending on the nature of the solid. The constant proportionality of this variation is concentrations is, however, a function of the solvent and change considerably of the different solvents for different solvents. Osmotic pressure. Osmotic pressure is related to the concept of diffusion osmosis, and it's defined for the solution tendency for a solution of a solution that is separated from the solvent by permeable membrane. The solid exerts osmotic pressure when faced with the solvent if it cannot pass through the membrane that separates them. We can also say that the osmotic pressure of the solution is equivalent to the mechanical pressure and it's need preventing entry of water and when it's separated by the solvent by a semi-permeable membrane. A relationship between the osmotic pressure and vapor pressure. Starting from the pure thermodynamic consideration, it's a possibly obtained to relationship between the osmotic pressure and the vapor pressure extend for vapor pressure from a solution. A constant temperature where the pressure external on the atmospheric and the transfer of the solvent to the solution has place because the molar free energy of the pure solvent uh, if zero is greater than the corresponding on one of the F1 solution to reach the equilibrium between the both of and stop the osmosis. It's necessary to increase the value of F to F1 by raising the external temperatures of the solution from 1 atmosphere to the pressure P. This is increased in free energy is F, and the condition of osmotic balance is established when, and we have the expression. It's all. Thank you for the attention.